Hello Year 9 and welcome to our next session. This time we're going to be looking at the national grid. So the first question we have then is, how exactly does electricity get to our homes? Well, it does so via something that we call the national grid. So the national grid is a national network of power lines, pylons, transformers, cables, everything it takes to get electricity from the power stations to our homes or businesses. The voltage leaving a power station is typically somewhere around 30,000 volts, but obviously we know the voltage coming to our homes is 230 volts. So the network also has to make sure that the voltage is changed on its journey. Normally in school we do a practical at this point looking at the transformer. It would look a little bit like the diagram here. We would have a soft iron core, usually made of two parts we call C cores. We'd have a primary coil around one. We're using insulated wires, which have plastic on the outside. And then we'd have a secondary coil, also insulated on the other side, so they're not at all connected. And the iron core isn't connected to the wires either because the plastic insulation keeps it separate. The first coil will go to the power pack, and the second coil will go to a multimeter so we can read the voltage coming off of it. So first of all, I will get you to connect it up as shown, and then I'd ask you to connect the power pack to DC and see what happens. Using DC then, the iron core will become magnetic. It's now an electromagnet, but you'd get absolutely no reading on the multimeter. In the second part of the practical, I'd now get you to change the power supply to AC and then see what happens. The soft iron core becomes magnetic again, but this time you would see a reading on the multimeter. So we find that this piece of kit, which we call a transformer, needs to be on AC in order for it to work. So the transformer is enabling a current from the first wire, the primary coil, to be induced, that's the key word we use, into another wire, that's the secondary coil, even though the wires aren't at all connected. The wires are insulated, so the current isn't transferred through the iron core. It is induced from one coil to the other. In the third part of the practical, I'd then get you to try changing the ratio of coils on the primary and secondary. So in this example, there are a lot more coils on the primary than there are on the secondary coil. I'd then get you to repeat it with fewer coils on the primary coil and more coils on the secondary and see if you get a difference. So we do get a difference. If your kit looks like the diagram here, where you've got more coils on the primary and fewer on the secondary, then the voltage that you get on the multimeter will be smaller than that from the power pack. It's stepped down. If you do it the other way around, where you've got more coils on the secondary than you have on the primary, then the voltage on the multimeter will be higher and the voltage is stepped up. So not only can this piece of kit get a current to induce from one coil to another, it can also change the voltage, even making it greater than that you started with. To summarise then, transformers can change voltages. They can either step it up or they can step it down. So we have step up or step down transformers. They only work using an AC supply. So we use them in the national grid to increase or decrease voltages. For example, when it leaves a power station, it leaves at around 30,000 volts and we step it up to a higher voltage. This means it's a lower current and it reduces energy losses as it travels through the cables. By the time we get to our homes, we want a much lower voltage so it's at a safer level. So it's stepped down again using a step-down transformer to 230 volts. So this diagram shows how the national grid works. We have a power station at one end. As it comes out of the power station, the electricity is stepped up to a high voltage. It's then transferred through the national grid, through the cables, across the pylons, and then as it gets towards our homes, it goes through a step-down transformer to bring the voltage down to a safe level. So there are two jobs that the national grid needs to fulfil. The first is it's a network that links up power, supplies, and our homes and businesses all over the country. The second job it fulfills is to ensure we always have enough electricity when we need it. It has to make sure that supply meets our demand. So why might demand increase? So we tend to use more electricity at night, obviously. We put all our lights on. We also use more electricity in the winter. Again, it gets darker earlier, so we use lights. We put the heating on. We're perhaps more likely to cook hot dinners. There are also peaks when we get home, for example. So we tend to come in, we all switch the lights on, we make our dinners at around 6 or 7 o'clock in the evening. And again, you'd find a similar peak in the morning when maybe we all get up and we put on electric showers or switch on our radios and so on. You even get peaks during particular events. You may find there's a lot of electricity being used during a big football match, or perhaps if there's a very popular TV show at the end or during the ad break, everybody goes into the kitchen and switches their kettles on and makes a cup of tea. So the national grid needs to be aware of this and plan for it. Okay, so now you've been through this lesson, I'd like you to have a look at the web links below. There's a YouTube for free science lessons, and there's also some BBC bite-sized pages you might find useful. I've attached a worksheet to show my homework with a mark scheme at the end, so you can have a go at some exam questions and then see how you did at the end. Finally, I'd like you to complete the quiz on Show My Homework so I can check your understanding. Okay, good luck with all of that, and next time we'll be doing electrical power.